There goes the second button. So double checking on YouTube. Yep. So we are live on YouTube's side too. So we got 2 minutes before noon time, and if anyone has any question, we can I can answer those questions right now, and then we'll get started in about 2 minutes.
I have a quick question.
Yeah.
Uh, are we gonna we're gonna go over the test today or no?
That was not part of the plan, but we can certainly do that if
Uh, I
anyone's
was just.
interested. Yeah, yeah.
We don't have to. And you said before, if I'm not mistaken, you said that um, if it's not likely that everyone's gonna finish all of the 11 questions from before.
Could you ask that again, Nick?
So the test was 11 questions, I believe, and I think a few people were saying they were having like a little bit of a hard time um, finishing. Did you notice if it ended up being like that, where there was like a couple of us that didn't necessarily finish? Do you feel like not all 11 questions will be counted?
I have not started to grade it yet. Um, but once I start to grade, or once I'm done grading, I would know the distribution of how how the points distribute, and then basically at that point I will make adjustments if necessary to kind of maintain the usual grade distribution of A B C D F.
Okay, cool.
Yeah, so that means if people know that their relative rank in class um, is relatively okay, I think their grade should be okay too. I cannot give
Yeah.
you the grade distribution that I'm targeting, but if you look up past grade distributions, which I think is public information for any class at a community college, that's basically the ballpark that I'll be shooting for.
Okay, cool.
Hmm. All right, so I think it is noontime, or slightly past. Okay, we're 10 seconds past the noon time, so I'm going to get started with today's lecture. As far as the exam is concerned, I think the 11 questions are fairly standardized type of questions. There are no super duper tricky questions, because they are all either related to relations or to CNF and proof by contradiction. There are different cases, okay? So there are various combination of relation properties and stuff like that. So there are certain variations, but otherwise they are very similar to the past exams and also the homework assignments. So I'm not going to spend too much time to work on the exam at this point. The kind of cool thing that I can do with this particular exam is when I get to it, okay, which is when I get to it, I can go ahead and share the actual key to each individual exam. So that's kind of a cool thing, because I was able to, when I generated the questions, I also generated the answers or the keys, and each file has its own keys. So as a result, I can actually share the key to the person who got that specific question. So that's one thing that I can do with this exam, and I expect to do about the same thing for the final exam. No promises, because the topics for the final exam is slightly different, so I may not be able to do exactly the same thing, meaning that I would have a key to distribute along with the question after the exam. Okay, but for exam two, definitely doable, and I will go ahead and do that. All right, so getting back to Pascal's identity, which is what you're seeing on your screen right now. Okay, and I have to keep an eye on the. Okay, all right. So I'm keeping an eye out on the text channel right now. So Pascal's identity. Okay, so Pascal's identity, the identity itself, is really the equality between. If you look at the screen here, is between this part and this part over here. That's Pascal's identity. That equality is known as Pascal's identity. So the question is, well, okay, first of all, there are two questions. One is what is the significance of Pascal's identity? That's one. And then the second one is, okay, how does it work? How does the proof itself work? Okay, so we'll answer the second question first, okay, which is, mechanically, how does this proof work? And you can see that this is basically all the steps involved in the proof. And and for the most part, it's really just algebra, okay? But it's not your usual daily algebra. It does borrow some tricks from working with factorials, okay? Because when you work with factorials, there are certain types of simplifications and expansions that are not usually useful in general algebra, okay? But it is still derived from general algebra. So let's go ahead and quickly go through this proof, going from step 1 all the way to step 10 over here. So step 1, okay, is just an expansion. If you look at the left-hand side, which is the combination, and if you look at the right-hand side, which is expressed in factorials, that's really just based on the definition of combinations or the number of combinations. Going from the first line to the second line, is a fairly minor manipulation. So in this part over here, okay, it's a little bit harder for me to kind of point to where I want to highlight. So when you look at this sub-expression, which is n minus in parentheses k minus 1, I just use your regular algebra and turn it into n minus k, the whole thing plus 1. Okay, and that's pretty standard because the 1 has double negation. One negation is inside the parentheses and the other negation is outside of the parentheses. So when we use associative law, and move that constant out of the nested subtraction, it becomes a plus. Okay, so that's not really a big surprise. And then from the second line to the third line, we work with um, this a little bit in the sense that we multiply both the numerator and also the denominator by k. So if you multiply the numerator, which is just n factorial by k, that's not much you can do about it. Okay, it just becomes n factorial times k. But when you multiply k to the denominator has k minus 1 the whole thing factorial already, which means it's k minus 1 times k minus 2 times k minus 3 and so on, all the way down to 1 or 0. Okay, either one works. But if you just multiply that whole thing by k, it becomes k factorial. And that's why, I can now say, oh, okay, the denominator now has k factorial. Are there any questions about this particular step? Because we're going to use this trick a few times in this proof. Okay, no questions. All right, so we are moving on from 3 to 4. So
Sorry,
to
I was unmuted. I did. Could you explain step 2 to step 3 again, please?
Okay, one has k minus 1, the whole thing factorial, which is k
Right.
minus 1 times k minus 2 all the way down to 1. And then when we multiply this with k, because we are multiplying k divided by k to the entire thing, so the denominator also gets multiplied by k. So if you multiply k with k minus 1, the whole thing factorial, you get k factorial.
Hmm.
Is that
Oh, right. Yeah. All
okay?
right.
All right. So going from line 3 to line 4, um, it's just a reordering of how. Uh, nope, I take one term out of the big denominator. So when you look at this particular denominator, the first term of this entire factorial is n minus k plus 1. Okay, so I separate that item by itself and then move it to the denominator just for the upper part of the overall fraction. So without that term, it becomes just n minus k factorial. Is that okay? Does everybody understand what I just did here? I broke off one
I
term.
do not understand.
Okay, so I broke off the largest term or the first term of n minus k plus 1 factorial, which is n minus k plus 1. And then instead of including it in the overall denominator, which is this entire thing, I just say, well, if I divide the numerator by this part first and then divide that entire overall numerator by this thing here, I still get the same thing. I just reordered the division by n minus k plus 1. so that it is no longer a part of the factorial. Is that okay?
I think so.
All right,
There,
go
so
ahead.
you just broke it off and put it in the denominator of the overall numerator.
Right.
So
So the idea
no
is
mathematical trickery necessarily. It's just
no.
we simply arrived at the same conclusion if I do.
Okay,
Right.
so it goes like this, right? N minus k, the whole thing plus 1 factorial is n minus k plus 1 times n minus k times n minus k minus 1, blah, 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 all the way to 1, right? I mean, that's basically the definition of factorial. So when I look at this portion here, I go like, hey, this is just n minus k factorial. So this whole thing becomes n minus k plus 1 by itself and then n minus k factorial. Is that okay?
All right.
So this part, I keep it in the overall denominator over here, but then this part over here, I broke it out so that I only associate it with the numerator.
Okay, what do you mean by breakout? We just divided the overall denominator so it ends up in the
Okay,
overall
so
numerator or something?
if you look at a fraction, right? Okay, let's say you have a over b times c. Okay, so when you look at this
Okay.
fraction, you can also look at it as, okay, keeping the fraction symbol over here, but you can look at this as a divided by, a divided by b first, and then the whole thing divided by c, right? It's just the same. It really is expressing the same thing because we are dividing a by b and then the whole thing divided by c, right? So whether you divide it by b first and then you divide it by c, or you divide a by the product of b times c, it doesn't really matter from the mathematical perspective. Does that make sense?
Would you also get the same result if it were a divided by b, c divided by
Yes.
b?
Yes,
All
because if
right.
you look at it from a even more abstract perspective, a divided by the whole thing, which is b times c, the product, is really the same thing as a divided by b first, and then the whole thing divided by c, right?
All right.
So I'm just using this to, so basically our a is, in this case, our a is this part over here, and then the b that I broke apart, okay, well, not entirely, but the b and the c, okay, b is this part, which is a single term, and then c is n minus k factorial. That's basically what I did with these steps, going from step 3 to step 4. So are we good?
I believe so, yeah.
Okay. So you can spend a little bit more time to look into the algebraic, part of the derivation, and if you cannot figure it out, then we can go ahead and talk about that. Okay. So from 4 to 5, okay, from 4 to 5, the right hand side is not changed. Okay, so when you look at the right hand side of the addition, there's no change. But when you look at the left hand side, okay, it is changed a little bit. And basically, I apply not really exactly the same trick, but I multiply n factorial by 1, except that 1 is expressed as n minus k plus 1 divided by n minus k plus 1. So if you look into this portion here, let me see if I can just zoom in a few times. So it's easier for me to select which portion here. So when you look at n minus k plus 1 divided by n minus k plus 1, it really is just 1. So I'm just saying, hey, n factorial is the same thing as n factorial plus 1, so it doesn't make any change. So are we good so far from 4 to 5? Yes? Okay. So assuming from 4 to 5 is okay, now we go from 5 to 6. Okay. So going from 5 to 6 is recognizing n minus k plus 1 divided by, and well, okay, combining n minus k plus 1 and k factorial n minus k factorial, the two sides now have the same common denominator, which means now we can concatenate the numerators. So the numerators that I'm referring to is this portion, which is a numerator, and also this portion here as a numerator. So that's how we can combine the two numerators because they share the same denominator already. So the denominator is really, the product of n minus k plus 1 and k factorial and n minus k factorial. So that is combined here. That's going from step 5 to step 6. Going from 6 to 7. So going from 6 to 7 is really just moving n minus k plus 1 into the into the overall denominator. But since we have n minus k factorial times n minus k plus 1, so all we do now is to say, hey, there's an easier way to say that. It is really just n minus k plus 1, the whole thing factorial. So the whole thing starts to look a little bit simpler. The other thing that we also did from line 6 to line 7 is I expanded this particular thing. I used the law of distribution in normal algebra and broke it up into these two parts. But once we have these two parts that was originally factored, now you can recognize that, hey, we have a subtraction of n factorial k, and then we add it back to the entire thing so that that portion just cancels out. So now we just have n plus 1 factorial as the numerator, and then the denominator now has k factorial times n minus k plus 1 factorial. So we have two more steps to go. The next step is really just to move the plus 1 so that it is right next to the n. So we have n plus 1, the whole thing, minus k. So that's really just a simple, algebraic type of manipulation. But that last step is important because now we can recognize the pattern of, oh, this whole thing is really just n plus 1, choose k, because that is the format of how we express combination. All right, so are there any questions about this entire derivation? If you have minor issues with the algebraic part, you can try to figure it out first. If you absolutely cannot figure it out, then go ahead and text me, after class, so I can help you with the algebra part. But are there any questions about this derivation? No questions? All right. So as I said, okay, the only trick that I use in this type of derivation is to say, k factorial can be broken up as k times k minus 1 factorial. Okay, I'm just using the recursive definition of factorial, and that really helped to, simplify a few steps and also make it possible to combine the right hand side and the left hand side, and then we end up with the conclusion of n plus 1 choose k. So now the question is, all right, so why is this important? Okay, have we seen anything like this before? That's the question, okay? So what we'll do is we're going to look at something that we already looked at last time, but this time when we look at it, we'll use a slightly different perspective, okay? So we'll start to label the rows in a Pascal triangle, okay? So we'll start with 0, okay? And then we have 1, 2, 3, 4. Okay, we'll work it up to 5. Okay, that's okay. And these turn out to be the k. Okay, so these are the k columns. Okay, and then horizontally we'll have the n. Okay, so we have n equaling to you can start with 0. 1, 2, 3, 4, 5 again. Okay. So this particular cell here is asking, what is 0 choose 0? Well, 0 choose 0 is basically asking, how many ways can we select nothing out of nothing where the order is not important? Well, the answer is 1. Okay, does anyone want to talk about this? Why there's only one way to choose nothing out of a set of nothing? Okay, all right, so moving on to the next row. Okay, so the next row has 2 items because now we got one thing. So we have n, I think I got the n and the k flipped. Yeah, I think I got them flipped. This is supposed to be k. This is supposed to be n. There we go. So on the second row here, we're saying I got one thing in my bag, okay? And how many ways can we choose nothing out of that bag where ordering is not important? There's only one way, okay? Just don't choose anything. Don't take anything out of the bag. And then we ask a second question, which is, I only want to get one thing out of that bag that only has one thing. How many ways can I choose one thing out of a bag that only has one thing? The answer is quite obvious. It is one. Okay. So now we move on to this row here where n equals to 2. So when n equals to 2, I have two things in the bag. And I ask again, how many ways can I choose nothing out of a bag that has two items? The answer is there's only one way, okay? Which is not to pick anything out of the bag. How many ways can I choose two things out of a bag that has two things? Well, interestingly, there are two ways to do it, okay? Where the ordering is nope, I take it back. How many ways can I choose one thing? Okay, I did not pay attention to the K. So how many ways can I choose one thing out of a bag that has two things where ordering is not important? Well, there are exactly two ways to do it. So let's say I have A and B in a bag. If I need to choose only one out of those two, then I can choose just A, okay, or I can just choose B, and that's why there are two ways. And then the next item is how many ways can we choose two things out of a bag that has two items where ordering is not important, which is very important. Because if ordering is not important, then we only have one way to choose two things out of a bag that has two items, because you just say, okay, give me the bag, and then you pour everything in the bag into a container, and that's the way. Okay, that's only one way to do it. But you can probably already see that this is actually Pascal's triangle. Okay, so this is 1, 3, 3, 1, and the next one is 1, 6, 1, 4, 6, 4, 1, and then I'll just work out one more row here. Okay, this is 1, 5, 10, 5, oops, 10, 10, there are two tens, and then a 5, and then a 1. So, all right, this is Pascal's triangle, and I'm just assigning the row number as n, starting with 0, and I'm assigning the column number as k, starting also with 0. So, what is the big deal here? Why is this related to Pascal's identity? Does anyone want to help me figure this out? Okay, how does this have anything to do with Pascal's identity? Come on, you guys. Nobody. Okay. Well, if no one wants to talk about this, what about this? Okay, I look at n as the row number. Okay, so n is the row number. This is row number 0, row number 1, 2, 3, 4, and so on. And then I look at k as the column number on a particular row. So when you relate this part over here, okay, and this part over here, it's basically saying if you want to figure out the value of a particular cell, let's pick this guy over here, okay? It's saying this is row n plus 1. In order to figure out column k of row n plus 1, let's go back to the previous column, because we have to refer to these two, which is on the previous row. So in this case, we're referring to the row when n equals to 3. But which columns of that row should we look into? Well, the first one is column k itself. So this 6 needs to look up this 3. But we also want to look up the column right before, which is k minus 1. So 3 minus, so the previous column is this of 3 over here. So it kind of explains why 3 plus 3 makes up this particular 6 over here in Pascal's triangle. In other words, Pascal's identity is the mathematical basis behind Pascal's triangle. This is why it works. Are we okay with this concept so far? Does everybody relate? Okay, forget about the actual mechanism of the proof for now. Okay, so forget about step 1 all the way to step 10. If you just look at Pascal's identity itself, that is the reason why Pascal's triangle works. Because by adding up two values of the previous row, you get the value of the next row. This is why it works. All right. Do we have any questions? Because if there are any questions about the conceptual part of why Pascal's identity is related to Pascal's triangle, this would be a good time to ask. We don't have any questions? All right. All right, so without any questions, we're going to now move on to the binomial theorem. So the binomial theorem is saying if you want to make a polynomial, okay, which is p plus q to the power of n, that whole thing boils down to the summation of I going from 0 to n, where each term in the summation is n choose I p to the power of I q to the power of n minus 1. Okay, that's the theorem. This backtick over here, that is that's a typo. Okay, I accidentally put in an extra backtick, but it is not a part of the expression. Okay, so now we want to prove the binomial theorem. Okay, so this is the binomial theorem. It is a direct proof. It's not a indirect proof, but it is also a proof that uses a technique that we have not been talking about that is actually a part of the syllabus of this class. It is called proof by induction. So the binomial theorem is using a technique called proof by induction. So how many people have heard of proof by induction before, either in CISP 430 or maybe in another math class?
Pre-calculus and calculus.
Oh, pre-calc. Interesting. Okay. So some people have some exposure to proof by induction already, but I'm not going to make that assumption, even though if it is a topic in pre-calc, which is a prerequisite of CISP 440, that means everybody should have some exposure to proof by induction. So proof by induction is really quite interesting. Okay, so let me just summarize what it looks like in terms of the format of proof by induction. So we have proof by induction as a template. So what you want to do, or what the theorem typically would do, okay, the theorem says for all k in a particular set, and the set in this case typically would be something like a natural number set, where you have a natural end to that particular set, and it has to be a discrete set, which means you can just add one to move on to the next element. So I'm just going to use natural number here, but you can definitely see how this can work also with integers. Basically, you break up the set of integers into the non-negative integers as well as the positive integers. Then you can treat each one as if it is a set of natural number where the sign is flipped for one of them and the other one is not flipped. Okay, so the general idea is like this. Okay, so I'll just use a natural number in this case as a template. So for every k in n, some kind of theorem, I'll call it p of k, is true. Okay, so in this case, I'm actually giving you a preview of predicate calculus. Okay, the uppercase p in this case is not the probability, it is called a predicate. So now let me go back and talk about what is a predicate. Okay, so p of k is a predicate, which means it is just a function that returns Boolean as a value type, and it takes k as a parameter. Okay, so this is how we can relate a predicate to programming concepts. The predicate p, which takes a parameter of k, is really boiling down to something that looks like this. Okay, it's a function that returns a bool. The function name is k. It's p. Is taking a natural number as a parameter, which is k, and that's it. Okay. Now, what is inside the dot dot dot? We really don't care. Okay. The bottom line is it is parameterized by k, which is an unsigned, which is the closest thing we have as a natural number, and then p as a function is returning a Boolean type But exactly how it computes the return value, that we are not concerned about at this point because we are looking at proof by induction from a fairly high level and abstract way. Okay, so the theorem typically can be expressed as a universal quantifier of a particular value over a set, and typically the set is a natural number or something that is at least countable. Okay, and and whatever p as a predicate is has to be true for every single k value in the set, in this case the natural number. Okay, all right, so this is what we need to prove. The question is, how do we prove it? So proof by induction typically involves, well, I should not say typically, always involves the base case. Okay, so the base case is, in this case, we say p of 0 is true. Okay, um, and prove that using typical proof techniques. So that means, to prove that p of 0 is true, you just use regular algebra. For the most part, p of 0, or the base case, can be proven without the use of much math. Okay, it's really just looking at the definition of p, and then you substitute 0 in place of k, and then just work it out, and you will find that, oh, okay, that's naturally true. Okay, so that's the base case. Base case is straightforward, usually pretty easy to do. Okay, the next step is called the induction step. The induction step has two steps. Okay, so part one of induction step is to say, assume p of k, assume p of k is true for all values from 0 to some n, let's call it n minus 1. Okay, it's an assumption. Okay, this is the really awkward part of proof by induction, is it seems like we are using an assumption that is not founded in order to formulate the actual proof. Okay, but later on I'll tell you why exactly it is not unfounded, but it's the assumption. So step two is to say, use the induction assumption to prove that p of n is also true. That's it. Okay, so if you can make the assumption that p of 0, p of 1, p of 2, all the way up to p of n minus 1 are all true, then go ahead and use that assumption to prove that p of n is also true. Okay, so if you can do this, okay, if you can perform step 2 of the induction step, then you would have proven proof by induction entirely. Okay, so let's work with something that's a little bit simpler compared to the binomial theorem first, just so that we get a taste of what it is, what it's like. Okay, so we'll go ahead and say, we'll define a function. Okay, this is just a function definition. We'll define f as a recursive definition, and we say f of 0 is in fact by definition 0. Okay, so don't try to prove this. This is just how f is defined. F of n, where n is greater than 0, is defined as f of n minus 1, and this time I have to remember what it looks like, plus 2n minus 1. Okay, and this is the recursive definition of n for n greater than 0. Okay, so first of all, are there any questions about the definition of f as a recursive definition? For those of you who say, well, can you turn this into a program because I can read C code? Well, quite easily. Okay, I'm just counting parentheses right now. Everything looks good. Okay. Okay, so either using the mathematical definition or using the program definition. Do we have any questions about the definition of n? Okay, I don't see any questions in the text area. All right, so shall we move on? Okay, so moving on, now I have to state the theorem. Okay, this is the theorem. The theorem says for all let's see, which letter should I pick? Well, let's pick K. For all k in n, which is the set of all natural numbers, the following is true. Okay, f of k is really the same thing as k squared. I'm using this as k squared, or better yet, I'll just say k times k. Okay, this is my theorem. Okay, my theorem is just saying that, oh, this is just a fancy way to recursively define squared. Do we have any questions about how the theorem relates to the definition of f? No questions? All right. So now how do we prove this? Okay, so now we want to look into a proof by induction. Okay, so just reading the template from the same text editor, can someone quote, what is the first step? What should I do first to prove this? What is the first step? What is the first step? What is the name of it? Or better yet, okay, let's relate this back to the discussion earlier. What is P as a predicate? How do we define P in this case? Well, the P is defined, the definition of P has to do with the theorem itself. So this is basically the core of the predicate. Okay, this has to be true for all the values of k when where k is a natural number. So if I want to go back and relate this to the previous thing, okay, the predicate P in this case is to say f of k is the same as k times k. That is how we define the predicate in this case. Do we have any questions about the application of the template of proof by induction to this actual case of proof by induction? Is that's okay with everybody? Because if you're not entirely sure, about any concept related to proof by induction, this would be a good time to ask a question. All right, so we don't have any questions. I'm gonna move on. All right, so now we have to work with the base case first. So the base case is saying, okay, TAC, can you show me that P of 0 is true? Well, let's check out what is P of 0 saying. Okay, P of 0 is asking, is f of 0 the same as 0 times 0? Okay, well, is that true or not? Well, let's figure out. Because f itself, okay, I'm just moving the cursor to the non-recursive part of how f is defined, which is this here using the mathematical notation, or if you use the C code, it is related to this portion over here. When n does equal to 0, we just return 0. Okay, it is non-recursive. So now we can go back to here and say f of 0 evaluates to 0, which is then the same thing as 0 times 0. Now, it is really important to not just say that f of 0 is just 0 and think that we are done with it. Okay, you actually have to relate f of 0 is by definition the same thing as 0, but at the same time 0 does equal to 0 times 0, because that is the format of what P is trying to express, because P is trying to relate f of k to k times k. So even though it is obvious that 0 times 0 is 0, we still need to relate the constant to the format that is in the definition. Okay, so now the base case is proven. Okay, the base case is true. Okay, so now we move on to the second step, which is the more confusing one, which is the induction step. So the induction step, going back to line 44, also has two steps on its own. The first one is assume P of k is true for all values from 0 to n minus 1. Okay, which is basically saying f of 0 is 0 times 0. F of 1, whoops, is 1 times 1 dot 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 all the way to f of n minus 1 equals to n minus 1 times n minus 1. That is the assumption. Okay, I know that we have only proven the base case. The second one is somewhat obvious too, but we don't even have to prove this one. Okay, we just say it's an assumption. Okay, we assume it works. And where do we stop with the assumption? For some n, we assume that f of n minus 1 equals to n minus 1 times n minus 1 is also true. And there's no exact value for this n here. We just say that, let's just say there is some n out there where the theorem is true all the way up to that n minus 1. Okay, that is the assumption. So step 2 is to basically say, using the assumption, prove that f of n is n times n. Okay, so how do we do this, right? So typically, in step 2 of the induction step, we make use of the recursive nature of the function. Okay, so we now say f of n is by definition, by its recursive definition, is f of n minus 1 plus 2 times n minus 1. Now, how do we know this? Okay, how do we know this claim that we quoted on line 76? It has to do with line 50. Line 50 is basically still defining f, so this is something that we don't have to prove. Okay, line 50 is not subject to proof because it is a definition. It is given to you and say run with this. Okay, do not question this, just run with it. Okay, so this first step here, okay, on line 76 does not need to be proven because I'm just using the recursive definition of f. Okay, then we look at this and then we say, we know what is f of n minus 1 because we have the assumption from before. Okay, so if you look at the assumption or the expansion of the assumption on line 73, we say, hey, using the assumption, we know that this is the same as n minus 1 times n minus 1. F of n minus 1 is n minus 1 times n minus 1 because the assumption says assume that p of k works all the way to p of n minus 1. So this is the result of that assumption. Okay, but don't forget to add 2n and then subtract 1 at the end. Okay, so now we look at this polynomial and we expand it. So now we get n times n minus 2n, right, plus 1. Okay, that is just coming from n minus 1, the whole thing squared. Then we have to add the 2n and then subtract 1 because that is a part of the definition of f of n. So without doing a lot of explanation in algebra, we can all see how this subtraction of 1 is canceling this plus 1 over here, and how this plus 2n is canceling out this subtraction of 2n over here. So what we have now left is n times n. So now we have just proven that f of n is in fact n times n only if we can, if and only if we can make the assumption that p of k is true for all the values from 0 up to n minus 1. So that's it. This is the conclusion of proof by induction given an f that is defined this way. Do we have any questions? I'm sort of expecting people to have questions now. So go ahead. No questions? Cool. In a
No, I
way,
followed that pretty easily, actually.
nice. Okay, good. That's what I want to hear. So nobody has a problem of the first part of the induction step, making some assumptions. Nobody wants a visual image of how that works.
I mean, of course I
Alexander
do.
seems to have a question about line 74 and onward.
Line 74. Okay. Well, that is really a
Or
part.
75 and onward, rather. Yeah.
Okay. Okay, so that's one question, and that there was another person who was trying to speak at the same time. Go ahead. Nobody. Okay. All right. So line 75 and so on is basically following the same template that we talked about here. Using the induction assumption, prove that P of n is also true. So that's exactly how I did it. Okay. Okay. Do we have any questions about line 76? Okay. Do we have any questions about line 77? For line 76? Because that is a part of how f is defined. Because the way I define f, which is all the way back here, is to look at f of n minus 1 plus 2n minus 1. Okay. Does the function have to be recursive? The answer is yes. Okay, this technique does not work or does not work well that I know of when the function involved in the proof is not recursive. So it does work only on recursive definitions because otherwise you cannot at some point it is recursive. Okay, it doesn't have to be literally recursive, but it has to be when you build upon the k, it's usually how should I put it? The okay, the reason why recursive works is because in order to use recursion, this is how we break up f of n, which is the new thing that we want to prove, using the assumption in the induction assumption. So you have to express the new case using a case that we have already assumed to be proven in the induction assumption. So recursion is just one way to express a relationship like that, but it's not the only way to do it. All right. So are we fully done with this example of proof by induction, which is from line 49 all the way to line 79?
I have one question. It's not really specific to this proof. It's about induction.
Uh-huh.
It's slightly general.
Uh-huh.
So I get how it works and how to use it and all that stuff,
Mm-hmm.
but just my brain gets caught up on the little details of. So we're assuming that it's true in the k case, and then we're proving it for the next case, right? The k plus 1 for
Yes.
any k.
Yes. Mm-hmm.
So I kind of just don't see necessarily, like I know it's true, but I'm not making the connection of how it proves the k case. Like I get that it proves the k plus 1 or it relates them,
Mm-hmm.
but
Mm-hmm.
I'm not sure how it shows that it's exactly like true.
Okay, so I think I got what you're asking. So basically, you're asking, well, how do we get this one, right? How can we make an assumption like that? Is that kind of what you're asking, Nick?
I'm asking how. I think so.
Okay,
Oh yeah, yes.
okay,
Yeah, because we're saying assume it's true for all k. Yeah.
okay. So when you look at this, the highlighted, I guess, your theorem, you can basically say, how do we prove that? Well, that relies on f of n minus 2. Now, how do we? Okay, so this basically is this entire thing is p of n minus 1. Okay, which is just using the concept of a predicate to describe for k n minus 1, it is true. Okay. But how do we prove that one? We use the case of when k equals to n minus 2. How do we prove that one? We use the case when k equals to n minus 3, and so on. Do you see how we can kind of fold backwards until we get to
Yeah.
f of 0? Right?
Okay. Yeah. Oh yeah.
So we can basically apply the same reasoning, the same logic, the same algebra, for to prove f of n minus 1 equals to n minus 1 times n minus 1. But that would make use of the assumption of f of n minus 2 equals to n minus 2 squared. And then that would rely on the case when we have f of n minus 3 equals to n minus 3 squared, but that would make use of the case when we make use of f of n minus 4 equals to n minus 4 squared, and so on until we hit 0. Then we go like, oh, okay, we have just hit not really a dead end. We have just hit, solid gold in this case. We have hit the jackpot. This one is jackpot. This is easy, okay? F of 0 equals to 0, which is equaling to 0 times 0. We can prove that one easily. Then you can unfold all the steps back, all the way back to f of n equals to n squared. Is that okay?
Okay. I'm actually, I'm seeing it from the reverse way, but then how come usually when we do proof by induction, we're like, assume it's true for 0, and then we let k equal k plus 1 instead of going backwards?
It's really the same thing. All you're doing,
okay.
yeah, you're just re-expressing what is the next step a little bit differently. Okay, so you can choose and say we can make the assumption all the way up to case n, and now go ahead and prove the case n plus 1, or you can say we can assume the case is true all the way up to n minus 1. Now go ahead and prove for the case when it is n. It really is the same thing because it's just a step going from n minus 1 to n. It's also just a step going from n to n plus 1. We are not skipping steps. We are not hopping. We are just working our way down sequentially.
Okay. All right.
Okay. All right.
Yeah.
Cool. So for those of you who are kind of having a challenge to visualize, how proof by induction works, this is how we can look at this. Okay. So I'm going to use some kind of text pictures over here. Okay. And we'll do it this way. Okay. I think some of you will kind of enjoy this picture. Maybe, maybe not. Okay, this is a coconut tree. Alright, so here's a coconut tree, and over here is a cruise ship, and it has nothing to do with the coronavirus. Okay, so I'm not going to waste too much time on my artwork here. Okay, so here's a cruise ship, and there's a coconut tree, which is the island that I'm on. Okay, so now the question is, can I get to the cruise ship from the island? Okay, non-corona cruise ship. Yeah, that would be kind of nice. Okay, so TAC is originally over here. Okay, and I want to go all the way to the cruise ship over here. Okay, so you can look at this as quote-unquote the proof. So what is the theorem in this case? Okay, the theorem is TAC can in fact get to the cruise ship. What is given? Okay, what is given is 1, TAC is on the island right now, and 2, he can always find a sea turtle who would move just within a step ahead of TAC. Is that okay? That's the assumption. Okay, that's our f. That's our function f, or our predicate. Is TAC is originally, okay, to begin with, TAC is standing on the island, and then 2, when he is stepping off of the island, he can always find a sea turtle to move exactly just one step ahead of him. That is the assumption. Is that okay? So we can now use proof by induction. Okay, so proof by induction says, do we have a base case? The answer is, oh yeah, we have a base case. This is the base case. Okay, TAC standing on the island is our base case. He is not sinking into the ocean. He's not drowning. Okay, that's our base case. What is our induction step? The induction step is a little bit tricky because what the induction step is saying is, if TAC is standing on, okay, a sea turtle, okay, then he can always do another step and step on another sea turtle within a step of him. So tag can go from here to over here. That is the induction step. Assuming that tag is standing either on the island or the back of a sea turtle, he can always take one step forward in the direction of the cruise ship. That is the induction step. Okay? Does everybody kind of get this picture, generally speaking?
Yeah.
Okay. And that's it. Okay? And if I can prove this, okay, if I can prove that I can always move one step forward, going from the back of one sea turtle to another sea turtle, then I have finished my proof that I will eventually reach the cruise ship. Yes, Carol is absolutely right, but this is a colorful fantasy that we can actually kind of imagine. Just kind of feel the sea breeze and breathe in the ocean spray and the sun. Yes. So basically that is the proof. Okay, this is the proof. Is the key to the proof is if I make the assumption. Yes, Brenda, that's a very good, nice picture. But which of the variable others is the sand? Okay, the sand is the base case. Okay, the base case is you're already given that I'm standing on the island at this point. So the sea turtles have gaps, but it's still discrete. Okay, when I walk from the back of one sea turtle to the next one, that is the induction step. That is the one step between the values. It is the k versus the k plus 1, or the n versus the n plus 1. I'm not sure, does that answer address Peter's concern? I cannot hop over multiple turtles at the same time. It's always the next one. That is a tricky question. Okay, so Peter's question is induction not possible if we're dealing with something that is non-discrete? So it depends on what you call discrete and what you do not call discrete. So the numbers that we're dealing with do not have to be necessarily discrete, but the proof have to have discrete steps. Okay, so those two things are separate. I can give you an example. Okay, in calculus, okay, you have the first derivation, you have the second derivation, you have the third derivation, and so on. So even though when you look at d of fx divided by dx, okay, this is not discrete math. Okay, this is continuous stuff. Okay, which we don't deal with in this class because x is in a how should we put it? So x is a continuous domain. Okay, it is not a discrete domain for x. Okay, but when you look at a proof that involve multiple steps of derivation, like relating the nth derivation of, okay, it's hard to express it here, but if you're looking at the nth derivation of f of x over dx, and you want to relate this to some complicated expression that involves d of the n minus 1 derivation of f of x divided by fx, then it can still be using the technique of proof by induction, because in this particular case, even though x is continuous, f of x itself is continuous, but the nth step of derivation is discrete. So I'm not sure whether this is answering Peter's question or not. Some portion of it has to be discrete, but it doesn't have to be the numbers or the equations that has to be discrete. It can be, which derivation are we talking about that has to be discrete. Because you can look at the rate of change, you can look at the rate of change, you can look at the rate of change, or you can look at the rate of the rate of change, or you can look at the rate of the rate of the rate of change. That part is discrete, even though f of x itself is not discrete, it is continuous. Is that okay? Okay. Somebody mentioned that they first encountered this concept in pre-calc. So in that class, what was the context that they used to show proof by induction?
We were using it. So I can't remember exactly what we were using it for, but my pre-calculus teacher was Rudy Gennaro, and he does like everything like to the fullest. So we were using it with vectors, matrices, like with anything that needed to be proven.
Okay, that's interesting because when you use matrices or in linear algebra, proof by induction can potentially be used because you can look at a matrix of size n times n to contain a submatrix of n minus 1 times n minus 1. Now obviously you have some additional rows and some additional columns that you have to kind of one additional row and one additional column to be exact that you have to add to make the new matrix, but you can potentially use proof by induction using in linear algebra the same way basically. Yep.
Now that I think about it, where we most used it is he would just say, given this, prove this.
Okay. Interesting. So the professor is already giving you the induction step of what assumption you can use, and then you're just using that to move on to the next step. Is that correct, Nick?
Yeah, usually it's very like formulaic. You just assume for k and then k plus 1, and usually just have to use algebra to find, to make it look right for the.
Okay, gotcha. Okay, very cool. So the next question that we have, okay, not going back to the lecture notes just yet, okay, because we can always get back to section 4.2. It really is, once we understand proof by induction, section 4.2 is really just a big algebraic type of exercise, okay, because the core concept or the structure of proof by induction is far more important than the binomial theorem proof itself. Okay, it is the structure of the proof that is important. It's also why proof by induction is so useful in computer science that we kind of have to understand. Okay, because I want you guys to be able to apply proof by induction or the concepts involved in proof by induction when you are just checking your programs. Okay, when you write the program in CISP 430, how do you know your program is working? How do you check that your program is correct? Okay, that is the question. Okay, so to address that concern, I will state one thing. Okay, every iterative algorithm can be written as a recursive algorithm. Okay, so they're basically functionally equivalent. Okay, if I give you a programming language that has no loops, okay, there's no while, there's no for, there's no do while, all it has is function calls and conditional statements. Okay, and there are actual programming languages like that. Like Lisp is one of those programming languages. We typically call those quote unquote functional programming languages where you do not have any construct for repetition, but you do have the mechanism of doing recursive call. Okay? If I give you a programming language like that and I say, okay, here, this is a particular algorithm, we'll say bubble sort, okay, which involves loops. You can always convert bubble sort, which involves loops, into a recursive definition that has no loops in it. Okay. Now I can also take a recursive algorithm. Okay, and factorial is a pretty typical one. Okay, so I'm just gonna write factorial over here as a recursive algorithm. So factorial as a recursive algorithm is simply saying if n is 0, go ahead and return 1, otherwise returns n times f of n minus 1. Okay, that's a fairly standard way to define recursion. I mean the recursive definition of factorial. So if I say, okay, this is the recursive definition, turn it into a non-recursive definition. Well, it's fairly easy too, because you just say Following? Okay. So you just have to say, result is by default a 1, and depending on how you want to optimize 0 or 1 out of it, you can always say if n is greater than 1, and we perform the loop body here, which is result times equal to n, and then we decrement n, and then after this is all done, return result. Okay, so can everybody see how this is a recursive way to define factorial, and this is a kind of, I'm trying to find the right word to describe it. This is the more pedestrian way to define factorial. Okay, so can we see the equivalence between these two? Are there any questions about the equivalence of factorial from line implemented from line 103 to 106 versus the more iterative approach of line 108 to line 117? No questions? All right, cool. So this is just a quick demonstration of how things can be easily turned into recursive if we want to, or we can turn something that is recursive into something that is iterative. Okay, and that applies to complex algorithms too, like depth first search. If you have taken those classes already, depth first search, which is very easy to express recursively, can be done without using recursion. But then you have to manage a stack on your own using an array. But nonetheless, okay, it can be done. Okay. So what does that have anything to do with proof by induction? Okay. Well, proof by induction has to do with this. Okay. Any recursive subroutine is fairly easy to test if you use the same technique as proof by induction. Now, what do I mean by that? So you look at this function f here, and how are you going to test it? Well, you test it first with what? What value of n should you use as your first test case if you are going to test this factorial function?
0.
0, exactly, because 0 is the base case. Okay, there's only one base case in this case. Now, if you can't potentially have a function that have multiple base cases, that might actually exist, but you can, but nonetheless it is a finite. Okay, base cases are always a finite number, so you can just test all the finite base cases. Then what do? Then you say, well, if I know the base case is working, I just need to take this next step up. Okay, then you can work up to a certain number, or you can assume that it works up to a certain number, and then you just try to test the next one. So that makes the proof somewhat conclusive. Okay, if you can say this f of, let's say, f of 5 is working. Okay, you check it and then you test f of 6, and that seems to be correct too. That usually gives you a pretty good idea that this algorithm is in fact working, because it is using the induction step to help you prove that it is working. Now, throwing test cases at a program is not really the best way to validate a particular algorithm. The best way to prove that an algorithm is in fact working correctly is to prove it using mathematics. And proof by induction is a powerful proof technique when you want to use mathematics to prove the correctness of a recursive algorithm. And this is why proof by induction and recursive subroutine, right, as a writing style, they go really hand in hand, because one is mathematically saying, how can we prove this theorem is true? The other one is using a programming language to express the steps in order to get something done, but using recursion, as a form of repetition. So that's why these two things really go hand in hand, in terms of, if you want to mathematically prove or verify that an algorithm is correct, proof by induction is a great tool to do that. So are we doing okay so far in terms of why induction or proof by induction is a very useful technique in computer science?
I have just one question on how you were saying using the induction for recursive programs.
Mm-hmm.
So I definitely can see how that's useful when dealing with like a simple program like factorial, for example. You know, you
Mm-hmm.
can just be like, it's this or that. But
Mm-hmm.
sometimes the code could be more complex where you reach a base case which is easy to define, but maybe your non-base cases have like logic in them.
Okay.
That does that
So
kind of make sense?
I can give you another example. Just one step. Okay. So Carol has the same question basically. So let's look at something that is slightly more complex. Okay, I wouldn't say a whole lot more complex. And to illustrate it, I'm going to use string. Um, I can pick one or the other. Let's look at string and copy. Okay, I'm just looking up the prototype on the other side. Okay, there we go. So we have string and copy, char destination, const char source, and I'll just say unsigned n over here. Okay, so we look at string and copy, and if you're in CISP 440, this really is something that you should know already. Okay, string and copy, you will copy up to n characters from the string starting with source to the string starting with destination. Okay, so you look at this and you say, well, I can implement this. Okay, and it returns a char pointer because all it does is to return d. Okay, the parameter d is what it returns. Okay, so that's pretty easy. So we just say, yeah, let's go ahead and return d. Okay, so now the question is, what do we do to do the copying? Now, obviously, this is something that all of you, okay, in CISP 440 should be able to do in, I would say, 10 to 15 minutes, okay, because it's just a single loop with a condition. You just copy up to a certain point, okay. The question is, how do you turn this into a recursive implementation? Okay, so the recursive implementation, I'll work with the more pedestrian way to express this, and then we'll work with a more cryptic but concise way to work with this. Okay, so the more pedestrian way of to express this is to say, when do we stop? Okay, when do I not to do a single thing? Okay, well, there are two ways. Okay, when n equals to 0, I don't want to do a single thing. Okay, so I know this is not the usual way to write C code, okay, because you typically want to do something when the condition of if is true. But this is how we stop a recursion. Okay, we test the base case first. If the base case in this particular case is satisfied, I don't want to do a single thing. Okay, which means by the time we get to the else, we're going to have to say, okay, n is non-zero, and because n is unsigned, if it is non-zero, it is always greater than 0. It cannot be less than 0. So now we have another base case to check. Okay, well, what about what s is pointing to? Now, before we do any checking, we can already say, let's copy. Okay, let's copy 1 byte, like that. Now, I don't have to ask a single question before I make a copy, because even if s is pointing to a null character, I'm still supposed to copy that. Okay, so I would just do a copy first, then I ask a question. Then I ask, is s pointing to a null character or not? If it is not pointing to a null character, then we're going to recursively call the subroutine to say string and copy to d plus 1 from s plus 1 and copy up to n minus 1 characters. Okay, so from line 119 to line 133, that's one recursive definition of string and copy. So is that kind of helping you guys to understand how to turn something that is iterative into something that is recursive?
Yeah.
Okay, very good. Now, I understand string and copy is not complicated logic either, but it gives you another data point of how to do the conversion. Now, remember earlier I said, you can actually do a one-liner in this case to implement this entire thing. So this is how we can do it. Okay. I don't want to turn this into a C programming class, okay? But nonetheless, I still want to show you this because I think you guys should know how to do this, okay? Doesn't mean that it's a good idea to do it this way, okay? So we start with the return. In other words, this entire function has one single. Okay, I think Nick, your mic is still on, and we're hearing a lot of wind noise. Thank you. So we use a single return here. So the single return, first check what is n, okay? And if n does equal to 0, okay, we'll just go ahead and do absolutely nothing and return the d, okay? Then we ask, well, okay, now that we know n is non-zero, what decision-making process do we do? Well, as it turns out, we don't make a decision process yet, okay? We do one copy first. So this is where, this is a real good test of how well do you know C, okay? Because this is actually not a statement, okay? It's an assignment operator in C and C++. It is not a statement. So I would do this first, and this is not a typo either. I did intend to use a comma instead of a semicolon, okay? Then I ask this question, okay? What is s pointing to? Okay, if s is pointing to a null character, okay, then we'll go ahead and return d. Otherwise, we will recursively call string and copy d minus 1, d plus 1 is a parameter, s plus 1 is a parameter, n minus 1 as a parameter, and we'll just add 1 to whatever string and copy returns. And now I have to count parentheses to make sure I close all the open parentheses like that. This is the other way to express exactly the same logic. So if you're looking at line 138 and go like, what is that line doing? Can we really have a comma inside, parentheses? The answer is yes. As it turns out, comma, okay, let me highlight what we are talking about here. So as it turns out, comma is an operator in C and C++, okay? And parentheses combined with comma, allows you to specify a sequence of expressions where the expressions are evaluated from left to right, guaranteed, okay? So what the C compiler does in this case is to look at this as an expression, okay? It actually has a return value. The expression has a value, which is the right-hand side of the assignment, okay? Whatever asterisk s is the value of this particular expression. But after this, the C compiler goes like, oh, wait, hold on a second here, okay? This part here is not the value that we should be returning as the else part of the ternary expression, because we got a comma and there's a second part here. So this ternary expression, which is to the right-hand side of the comma, is the last expression of a comma-separated list of expressions. And that, in return, becomes the return value or the actual value of the entire comma-separated expression. This is how, I can combine, this is how I can kind of like collapse line 121 all the way to line 132 into one single expression, which also means in this case, if people say, oh, we don't really need a whole lot of new lines over here, well, you can always combine those new lines into this. That is actually a valid specification of how you can implement string and copy. So if you don't fully understand how how line 135 to line 138 works, you should still be able to understand how line 119 to 133 works. So do we have any questions regarding this implementation of string and copy? No questions? All right. So given this logic, okay, so I'm going to go back to the kind of more pedestrian implementation over here. So we look at this implementation and we say, well, how do you prove that this implementation is correct? Okay, mathematically, I'm not throwing test cases at it. Okay, if you just mathematically analyze the algorithm, how do you know that this is correct? Well, the first thing is we look at the base case. Okay, the base case says if n equals to 0, if I'm not allowed to copy even a single byte, what am I doing? I'm not doing any copying. This is the then portion, and the then portion is just an empty statement. I'm not doing a single thing, and I just return whatever d is, which is what the documentation specifies that we have to do. Okay, so done. Okay, we're done with one of the base cases. The other base case is, what if s is pointing to a null character? It's an empty string. Then this condition would be false, which means the else, which is doing absolutely nothing, is not going to copy anything in addition to what is already copied. So we just ended up copying the null character itself, and that meets all the requirements of the specification as well. So those two will form, combined will form the base case or base cases of string n copy. So now, if you want to say, but what about in general? Okay, if I have a string that is non-empty and n is non-zero, okay, how do we know that algorithm is going to work? Okay, so that now you can use proof by induction. In other words, you can now say, let's assume this step is working. Okay, if this step is working, okay, if we can copy up to n minus 1 characters, okay, and I'm copying the rest of the source string and the rest to the rest of the destination string correctly, is this algorithm going to work correctly? That really is the question. We make the assumption that the recursive call on line 129 is going to work already. So based on that assumption, we go like, well, if that substring is copied correctly, all I have to do is to make sure that the character that is pointed to by s is in fact copied to the character that is pointed to by d. Okay, we got room to do it. Okay, so yep, that part is definitely done when n does not equal to 0. Am I returning d? Yes, I am returning d. So what I just talked about is a very informal proof that this implementation of string n copy does work. Okay, mathematically it does work. And you can also see how I really just reapplied the template or the structure of proof by induction. So you can see how proof by induction and recursive subroutine definitions really go hand in hand. It makes the proof of the validation or the verification of an algorithm so much easier because of the use of proof by induction. So are we doing okay so far with this discussion? Because it applies not only to what we really set out to do today, which is the binomial theorem, which we are now out of time. We cannot really continue with this until Wednesday. But I think it's more important to understand how, why proof by induction and recursive algorithms are interesting ways to express something in computer science. So I hope at least we got that part. So are there any questions about recursion and how it relates to proof by induction?
I have some questions about recursion, but they mostly relate to the newest homework assignment.
The omega generator?
Yes.
Okay, so what about it?
Mostly,
Uh-huh.
just I'm pretty sure we're supposed to use recursion, and I did speak with some students on the matter beforehand, but I do not still quite get the mechanism of actually shuffling them in the order that they're.
Okay.
Say like we want 2 trials, and we the one we have in the
okay, so
homework thing where we have 2 trials and we choose 3 out of the alphabet.
Okay, so the first question is, how do you implement a set? Okay, so let me go back to the homework. Nope, that is. Okay, so we go back to counting first, okay, which is the notes related to the homework assignment.
Just real fast, since I'm gonna have to get out of here for another class.
Go ahead.
Can you post a couple ungraded questions that just ask for calculating probabilities or a number of things, just a lot of like a couple of counting type questions with probabilities.
Okay. Yeah, I will see if I'll see what I can find.
Okay. All right.
Yep.
Thanks.
Okay. Okay. So to go back to the earlier question, so there are a few things that we have to address first. The first one is how do you implement a set? T is a set, right? So and we have certain set operations here. There's the uh, basically remove everything in another set on this set. We need to find every single element of a particular set, make a loop out of it. So that's the first question: is what is your set implementation? The second question is once we have a set implementation, then the next question is, what is the recursive part of this particular algorithm? So the recursive part of this algorithm is this is the recursive call. Omega I is using omega I minus 1. It's basically it's recursion, except I becomes I minus 1, T becomes T minus the set with only E in it, and so on. Okay, but nonetheless, it is recursive. And we know when to stop also, right? Because we stop when it is omega 1 of something. So whatever T is, when we're working with omega 1, we just return whatever that set T is. So those are the setup. Okay, we need to be able to answer all of those questions first before we actually work on the algorithm itself, because it is implementation dependent. So when we look at those things, okay, so let me go back up to not this one. We go to here. So when we look at the homework assignment, or the description of the homework assignment, it gives you flexibility in terms of what programming languages you can use to implement it. So it says you can use Node.js, you can use Python, you can use Java, you can use C or C++. Okay, so all of these are available options. Depending on which one you choose, some already comes with some kind of implementation of a set, and others do not. Okay, so that's one thing that you have to consider is what programming language you want to use to implement this program, because if you use a particular programming language, it may be easier to express what a set is, how to perform the subtraction of a set. You can use two-dimensional arrays. Well, I'm not sure why it is two-dimensional. I can see how you can use a single-dimensional array. Okay, and then the other
I
thing
used
is,
a 2D array.
huh?
I used a 2D array.
You use a 2D array. So you
Yeah,
have to. So in that case, you have to look at the maximum or the longest experiment you can run, because you have to pre-allocate, or you can use new or malloc to dynamically allocate memory for that. So there, you can certainly do it that way too. Um, so let's just say that you want to. So I know we are out of lecture time. So if you want to drop out of the lecture, that's fine. The lecture is technically done, but I'm talking about techniques that people can use to implement this program. So if you think that might be interesting to you, you can stay on this channel. Okay. All right. So I'm going to use this area over here to basically describe a way to implement a set, because in this case we have a limitation here to make the implementation of that set pretty easy. Okay, because we only have the choices are only lowercase English letters, which there are 26 of, right? So we can basically say, let's not think about these as letter A to letter Z. Instead, we can think of these as, let's look at integer or unsigned integer 0 to unsigned integer 25, okay? Because those are the only things we have to keep track in a set. So one way to do that implementation, given this limitation, or given this how should I put it? Given this restriction, okay, in the homework assignment description, we can kind of do it this way, okay? So we can say we can basically use a uint32 underscore t as our set, Okay, so I'll just go ahead and use actual C syntax here. So we can do a type def, okay, uint 32 underscore t as our set. Oops. And to use that symbol, you have to pound include stdint.h, okay, in order to use this to refer to a 32-bit unsigned integer, which is all we need to implement a set. Okay. So in this case, okay, bit 0, okay, using comments, bit 0 indicates whether 0 is in a set or not. Okay, bit n, okay, bit n indicates whether n, okay, I must have a typo somewhere. Okay, there we go. Whether n is in a set or not. Okay, so this does require that you understand or at least remember how to do bitwise operations. So I look at a 32-bit integer and I look at each bit to mean the presence or the absence of an integer from 0 to 31. Okay, I know we only need up to 25, but we have actually some room to spare. Okay, that's the whole point. We have some room to spare. We can store 6 additional numbers that we do not need. Okay, so if you want to look at this and go, well, what would an empty set look like? Okay, so you say empty set. An empty set is just a 0, because when you specify the 32-bit integer 0, every single bit is a 0, which means every single number that it is representing from 0 to 31 are also missing. That's why we have an empty set. Okay, if you want to say, okay, singleton set, and then you specified a particular element value, and you want to make a set out of that particular element value, that really is just one left shifted by e times, because that is the bit position that becomes a 1 for that particular value of e. If e is 0, then it's 1 left shifted 0 times, which is really just 1, where bit 0 is a 1. If e equals to, let's say, 3, okay, then it is 1 left shifted 3 times, which is 8. But when you look at the value of 8 in binary, bit 3 is a 1, which is basically saying 3 is in the set. So this is how we can create a singleton set, which means it's a set with only one single element. If you want to make a test to check is a particular element in a particular set, okay, so you have the element as e, and then you have the set as s, okay, then it is really just a matter of doing a bitwise AND, which is ANDing s, bitwise AND, with 1 shifted by e times. Because s is basically a bit mask, where each bit position is indicating the presence or the absence of a particular elemental value. 1 shifted e times is specifying a 1 only for that one single bit position. The bitwise AND is going to say, well, if I just focus on one single bit position, is that a 0 or not? Because if that one single bit is a 0, then the bitwise AND is going to be all zeros, because 1 lefted shift e times only has one single bit of the 32 being a 1. Everything else is going to be a 0. So the bitwise AND is going to be a 0. So if you use this kind of implementation for a set, that's one way to do it. Okay, if you use C++, you do have a template class called set. Okay, uppercase SET with the square, the angle brackets. That's a template class. So that's one way to do it. If you use Node.js, it also has a built-in type called a set. Okay, so there are many different ways to implement what a set would look like. Okay, so now the next question. Okay, so let's go back to here. Let's see, where is the question? Oh, the definition. There we go. So once we know how to implement a set, the next question is, what about this thing here? What about the Cartesian product of something? Now that is a little bit difficult to deal with. Okay, it's difficult to deal with because um, if because technically speaking, the result of a Cartesian product is a set as well. Now that is where the simple-minded implementation that we just talked about here does not seem to work anymore. Okay, but on the other hand, you can use an array because of the way the recursive algorithm works out. Okay, you're gonna have to go get all the way in until you're working with omega 1 of t. Okay, so when you get down to omega 1 of t, then you already have all of the other choices made, because along the way, okay, so let's look at the definition over here. If you're working with omega I, okay, if this is the actual call that you're dealing with, it has to, before you can do the recursive call, you would have chosen one of the elements of the t that is passed to you already. So that means if you look at the chain of calls from omega I, then I minus 1, then I minus 2, all the way to omega I to omega 1, all of the previous invocations of omega have chosen their own characters already by the time we stop the recursion. So that means if you just use a single string, you can use a global variable. Okay, I know, we are not supposed to use global variables, but if you want to use a global variable, you can basically use the global variable to keep track of the characters that has been selected every single step along the way to omega 1. So by the time you get to omega 1, whatever choices is left in t is what you need to iterate over and then print that global variable string for each choice that omega 1 has to make. So this way you don't really have to track the Cartesian product, and therefore you don't have to deal with all the overhead that is unnecessary to deal with the Cartesian product. Because the homework assignment, if you go to, oh, not this, when you go to the homework assignment, the bottom line is, can you print out all of those permutations correctly? It doesn't mean that the permutations have to be internally stored individually. It's just that you have to be able to output those permutations. So I'm not sure whether that is helping or not. I'm going back to the text channel and see what questions we have here. So William has a question. Was there something that was to be provided in class for the assignment? Was that already covered? Well, it is up to you guys to choose how to do it. So what I'm doing right now is not sure how to display without sorting. You're not supposed to sort. You just have to go over every single one. Storing. Oh, okay, I misread. You only have to store one at a time. You don't have to store every single one of the Cartesian product.
I think what William's trying to say is that in your assignment you had like at the top of it you had something where you said you would be giving us pieces of code for parsing, I believe, or to intake whatever, like for the
Right.
command line, I believe.
I see. Okay, I got you. Okay. I did forget to mention that. Okay, so I did forget to mention that part. So that has to do with ARGV versus INGC. Okay, so I'm gonna I'm still recording. Yes, I'm still recording to YouTube as well, so I can show the rest of the class this too for people who are not currently here. Can you push back the assignment date? Yeah, I can push it back to Monday.
Thank
Right.
you for that.
Yep.
Yeah, thank you. It was just hard to like wrap my brain around
Okay.
the recursive method, in my opinion.
Oh, okay. So let me address the ARGC versus the ARGV thing first. Okay. So the code you can borrow, okay, is to use main usually comes with ARGC as the first argument, and then it has a const char star ARGV. Okay, so the other way to look at ARGV, or the values of the arguments, is an array of pointers to strings. Okay, it's an array of strings. Okay, that's the best way to put it. Okay, so because the assignment did not ask you to check, for errors, so you can kind of assume the ARGC is 3 to begin with. Okay, so you can basically say if ARGC equals to 3, then do the following. If not, you can just exit. Okay, so you can just say else do absolutely nothing and then return to 0. Okay, because the assumption is I will pass the correct number of parameters. So if ARGC is 3, we ignore the first one because ARGV bracket 0 is the path to the executable, okay, which is useless to us. Okay, for the homework assignment purposes, it is not of any use to us. So I'm just moving this aside so we can look at the code over here. So ARGV1 is a base 10 number, that is the number of trials. The other one is the number of choices. Okay, so trial is the first one, choices is the second one. Okay. All right, so at this point, we can assume that ARGV1, which is a string, is the number of trials, but it's a string in base 10. So you have to convert a string, which is a number in base 10, into an actual integer value. There are several ways to do this. You can use scanf is one. You can use
STI.
ATOI. ATOI can do it too. So let me move my window over here.
What's the benefit of doing that instead of just taking it as an int and then counting how many whatever characters you need, like char numbers? Like say if you put in 2 as your how many choices you want, then it just do AB. Because this way you just convert the string number of like 5 to that to the actual 5, and then you do that.
Okay, so well, the assignment is is using is describing that already, so I cannot change it at this point. But what I can do is to show you 2 functions that can do this, and then I'll go ahead and actually write a template. Like I'll give you the code to get to the number of trials and the number of experiments. Okay.
All right.
So this is the first function you can look into, which is ATOI. So ATOI is taking a string and it returns the actual integer value represented by the string as text. So that's one. You can also use scanf, which is a much more flexible function, but is an overkill for what we are doing. Okay, and it's much harder to use, so I would personally stay away from scanf unless you already know about it. Okay, so we use ATOI instead. So ATOI requires standard lib. Okay, so that's what we need. Okay, so I'm actually writing the function right now. Okay, so I'll start with omega.c pound include stdlib.h standard library, and then we'll pound include stdint, which is standard integer.h. So we need these 2 header files to get this part done. Well, actually, standard int is not exactly needed because I'm not implementing set at this point. Okay, so we'll go ahead and okay, so we say if. So remember to give main ARGC and also ARGV as its parameters. So for all this time when you use main without any parameters, you're just ignoring the parameters that are already passed to main. Okay, so until this time, until you actually get to this part of the class, there are some additional ones too, by the way. Besides ARGV, which are the arguments passed on the command line, you also get the environment variables, and also the number of environment variables, which are basically all the background stuff. If you just type set and press the enter key, in Linux at least, those are your environmental variables. So all of those things are actually passed to the program as well. So anyway, we'll just focus on this one here. If argc equals to 3, this is when we actually do something useful. Otherwise, we are not going to do anything at all. Okay, and you can just leave the code like this, because we can make the assumption that we pass the right number of arguments to the executable. So with argc equaling to 3, then we defined unsigned. This is the first one is the number of, what was it again? I cannot remember.
It's trials, then it's
Trials.
Trials. Yep, trials. Okay, so we say number of trials. Technically, this is an int, but since I'm not going to trick you guys by passing a negative value, if you say an unsigned, I think it should be okay as well. So ATOI, and then just give it ARGV1. Okay, and then you can use unsigned. The second one is number of choices, and the same thing, ATOI ARGV2 in this case. So this is all I'm gonna work out at this point. So now all I need to do is to printf. Okay, there are %u trials and %u choices. Now, if you want to use cout, that's fine, but I'm a C kind of person, so I'm using printf instead of cout. So the first one is num trials, the second one is num choices. Okay, and for the else, if you want to, you can print the error message if you want to. Okay, you can say error need exactly to need num trial and num choices. So I'm just giving myself an error message if I do not pass the correct number of parameters. So this is the entire program. Do we have any questions about the program itself that I can answer right now? No questions? Alright, so we'll go ahead and compile this and run it. So GCC, I'm not going to turn on all the error checking right now. Okay. And it gave me a bunch of warnings, which is expected. Oh, I need to pound include standard io.h because of printf. I think it created the executable anyway, but might as well just kind of fix it here. stdio.h. There we go. Compile, everything looks good. And now I can just run the command, okay? If I pass nothing to it, it's going to bark at me and go like, hey, we need the number of trials and the number of choices. If I give it one number, it's not happy about it. If I give it two numbers, it's happy. And this is how it can get the number of trials and the number of choices. So is that okay? I mean, does that help you guys get started with your code? It's really just this part. Huh?
So that's just to convert your string that you're going to give us, or to run our programs to convert the digits to ints in the string. That's all it does.
Yeah, that's all it does.
Okay.
So
that's for the
basically,
command line, I'm assuming.
your code goes here. There we go.
All right, that's good. That means I don't have to change like anything.
Nope. If you have implemented your logic correctly, this is really just you just basically slap this code into main, and then have this code to call the function that you have been writing already, or you have written already, and then you're done basically. Is that okay?
And for clarification, when we're if we use the recursive function, when we call the recursive function, as we head down to the tail, the base case, it's just going to be choosing a letter up until n-1, right? We'd be going.
You have to choose what. You can only choose what is left to you. Okay.
Right.
So let me give you.
But the point is, as we're going down as we're recursively the function recursively calls itself, it reaches that base case that there's nothing left to choose from.
No, you would never
Um,
be. You should never get to the point where you have nothing else to choose from. You should run out of trials. You should run out of number of trials, then you can stop. Okay, so it's up to you to decide. If I have one trial left, I would just do it, non-recursively, or you can say, if I have a trial of zero, then I really have nothing to do. That's up to you to decide. Okay, exactly how to stop the recursion. You can stop when there's zero trial left, which means you have absolutely nothing to do, or you can have one trial left, which means, okay, this last character is mine. I know how to specify the last character. So what I want to show you is how the invocations relate to each other, or one way to look at it. So let's just say that you have 5 choices and 3 trials. Okay, 5 choices and 3 trials, which means you have A, B, C, D, E as your choices for the first invocation of whatever recursive subroutine you're writing. Okay, so let's just say that out of these 5, you chose C. Okay, now you might say, well, why would I want to choose C instead of A? Okay, I'm just saying that, okay, because you have to go through all 5 in a loop in the first invocation. You basically have to say, for every element that is available to me, I'm choosing this at this point. Okay, so this is the first invocation of the subroutine. So by the time you get to the second invocation of the subroutine, the amount of choices you have left is just A, B, D, and E, because C is already chosen. So you have to make sure that when you pass the set to the second invocation, remove the element that the first invocation has chosen already. So let's just say that the second invocation, for whatever strange reason, chose to use D. Okay, so that means by the time you get to the third invocation, which can be the last or the second to the last invocation, you only have A, B, and E left as your choices. Okay, so this is where you can say, do you want to stop the recursion here, or do you want to do, the recursion when you have 0 trials left? So let's say that you want to optimize and say, when I only got 1 trial left, this is the end of the recursion. So as far as this invocation is concerned, you have to basically say, I have 3 options here. I can use the option A. So as soon as you choose the option A, print CDA out to standard out, because that is the permutation. But you also have a second option, which is B. So now you print, okay, so I'm going to make it more specific here. Print CDA, then print CDB, and you have a third option, which is E. So when this goes to E, or when the element that you want to consider as the last invocation gets to E, then you print CDE. Okay, so then you go back to the second invocation. Okay, in the second invocation, let's say E has not been explored yet, then you choose E. Then you have to call the third invocation again. This is not the continuation of the invocation. This is a brand spanking new invocation. The third invocation is new. So this time you have A, B, D as your choices. Okay, then you will print, A, B, and D. But the idea is a global string has already kept track of the C and the E, so when you only change the last character, now you know how to print the entire permutation, which is CEA in this case, and it's going to be print, come on, print CEB and then CED. So is that kind of giving you guys a clue of how to do this?
Sort of. Yeah, kind of. Honestly, everything that I think of is I just feel like it's just too complex. Like I thought at one point we had to use something like rand and like refine it so that it doesn't just take literally forever. And
No, this won't take too long. I mean, if you choose, okay, if you say 26, choose 26, yeah, that's gonna take a little bit of time. But you can always start with something like this, like you got 5 choices and then only 3 trials. In other words, when you're testing the algorithm, don't test it with something that is going to take a long time. You pick something that's simple, like 3 choices and 2 trials. That will give you a very short number of a small number of permutations. It is easy to check.
For the yeah, I have a question. For the ARGC, how would you implement it to where we check it? Would we just run it through like our CMD and then put it in the string and then it automatically like parse it from the code you gave us?
That's a good question. So are you using code blocks? I'm assuming using code
Yeah.
blocks or something like that. Okay.
Yeah, I'm
So-
using C++ code blocks.
Okay. So if you're using code blocks,
Like we have to like, make like a bat file that just automatically runs it and inputs a string for us.
okay, this is something that we did in CISP 310 for the floating
Yeah.
point homework assignment. Okay, I'm just moving the window so that you can see everything that is actually important. There we go. All right, so what we do is we're going to open a project. Okay, so we'll say new project. Okay, let me move this window over here so you guys can all see it. So we just need a regular command line C project, and it gives me a lot of options. Console application, there we go. Okay. And we can say next. Now, I just want a regular C program because I just want to illustrate how this works. So this is called Omega. Okay. And we can create this folder in temp. Okay, GCC, regular debug, everything is good. Finish, there we go. All right, so for the sources, I'm going to it automatically gives me a hello world main. So I'm just going to go back to the program that I have written here. Okay, mouse pad omega.c, because I just want to copy and paste it. That's all. So I'm gonna copy it off screen that you cannot see, and then paste it here. There we go. Okay, so all I did was to copy and paste the code that we looked at and tested already into a code blocks project. So to answer the question that was asked a little bit earlier, you go to project and then you go to set programs argument. This is where you can specify the number of so that this is what that dialog box looks like. So you go to program arguments and then you specify the 2 numbers that on the same line that we have just talked about. So if you want 2 trials and 4 choices, then you just type 2 and 4 over here, click OK, and then you go to debug, start. There we go. So that ran the whole program already. And does it print the output anywhere on the screen? That's just the debugger code blocks. It doesn't show the executable. It doesn't show the output. Well, I suppose we can put a breakpoint so it stops, right? So we'll put a breakpoint over here and then just test debug the code again. Okay, there we go. So if I put a breakpoint right at the return statement, then the console or the CMD window in Windows would still be up before we exit the program, and this is the output. There are 2 trials and 4 choices. So does that answer the question of how to set up the parameters? Okay.
Yeah, that makes sense. Thank you.
Yep. Any other questions? Oh, there are a few people posting things down here. And Carol said something about n minus the ASCII code of A. Yep, that converts the ASCII code of A to 0. So that way we can work with just integers. Do you mind uploading the information from mousepad? So are we referring to just the program or the entire discussion?
think she's talked about like the conversion, the code you had for like just that in general.
The conversion, all the notes, everything.
Never mind.
Yeah, I can. Let's see. I think we can do it here. I can do it in Discord. Yeah, Discord allows attachments, so I can upload omega.c.
Make sure it says txt at the end. I've had some problems with that.
Well, we'll see. This is the there we go. So I'm uploading omega.c. You should see it on Discord right now. And I'll go ahead and pin it so this way it doesn't get lost in all the further discussions. There we go. And then I'll go ahead and find my other window, which is here. Okay. And save it first. Then we'll post the file. So I'm going to save it in today's date, which is 2020-0420.txt. Uh-oh. Okay. And then post it over here. Oh. It's actually the my file selector is smarter than I am because it actually knows how to find the most recently accessed files, which is this one. Okay. Notes. Okay. Upload. It's interesting how Discord has a checkbox for spoiler. I should probably mark everything as spoiler. Yeah, go ahead.
No, it's fine.
Okay. So are you guys seeing the file, pinned at the top of Discord? If you just click on the little pin icon, can you see those?
2020-0420.txt is
Yep.
there. So is omega.c. Yes.
Yep. Can you guys open it? I just want to make sure that you guys can open it.
It is there. Yes.
Okay, excellent. Cool. How to access pinned message. Okay, so let me move the Discord screen to here. So this is a little pin symbol over here. Click on that, and it will show you all the pinned messages. So I guess it'll pin everything, the most recent on top, on the top. So that's why we can see omega.c and then the text file as the last item. Okay. Oh, okay. Yeah, Discord is actually pretty cool for certain things.
Hey, Professor Tack.
Yeah.
So for this assignment, a couple of questions here. So would you be willing to send out your solution after due?
Absolutely. I can in fact spell out two solutions. One implemented in Node.js and another one implemented in plain C.
Okay, I'll take both. That's fine. The way I did it was, I probably should have went back and looked at the module, but I did not do it like that at all.
You don't have to. Yeah, go ahead.
But the issue that I have with the way that I implemented it is it's all stored. Like all for mine to work, all the permutations get built basically in columns.
Ah, okay, I see. Okay, so that's why you have a two-dimensional array, so that each row is corresponding to one experiment outcome.
Yeah, so for me, basically, what my base case is all the choices. So if it's 3 choose, or if it's 5 choose 3, the base case is A, B, C, D, E as a column. And then I expand out like a tree for each of those. There's 4 ways to go like that. And so that makes it so it all has to be stored in memory. So I'm not even sure I could do 26 by 26.
Well, let's check out what is that number, 26 by 26. It's not too
It's
bad.
very large.
It is
I
large,
tried
but
it with my program.
But it's not 26 by 26 because it is
No,
26
I think it's like
factorial.
7 million.
Yeah, it's 26 factorial. Because if you have 26 A to Z to choose from, and then you have 26 trials in the experiment, then the total number of permutations is 26 factorial, which is a huge number. You probably don't have enough RAM for that.
That was my thing, right? My issue isn't time for the printing; it's the RAM.
Right, exactly. So that's why I would much prefer a way that is just generate a string, print it out, generate a string, print it out, generate a string, print it out, because that's all I want. I mean, that's all I want is just the output.
Yeah.
I don't need the actual representation of each one.
So maybe I'll try to, like, I'm gonna probably turn in this one and then try to redo it the other way. Another question I have is, so I have the one that I did, right, which is recursive, and I really was interested in the lecture you gave today about using induction to prove my program. And my question is, if I came up with something, would you be willing to give it a look and just tell me if it, kind of proves it or not?
Yeah, go ahead and send it my way. If I can work it out, and see understand your proof, we can do it.
Wait,
Okay.
so is that how you grade homework sometimes? Is using proof by induction if it's something simple for like your
No,
program classes, or no?
no. Yeah, with something like this, I just run the program and I have a few test cases. So I just run it through certain test cases. The programs that we write over here, can be reasonably tested just by testing the boundary conditions. In other words, I can test it with the same number of trials as there are number of choices, make sure that works, and then I can test it with like just one short. Okay, so you have 4 choices and only 3 trials. So if it does work in both cases, it's really hard to write a program, but it works. It will work in all of these test cases, but then with some other test cases, it does not work. Um, the but this type of testing does not work very well when it comes to TurboTax. Because in TurboTax, which has to reflect all the text code, which changes all the time, and there are special cases. I mean, if you look at the decision tree for tax code, it is insanely complicated because because the politicians intentionally make it insanely complicated. So for those things, you really do need like specific test cases for every single way to combine all of those conditions in reporting taxes. But the programs that we are writing only has got 2 parameters. I mean, it's relatively easy to test with just a few test cases. Does that
Just a clarifying question. I'm sorry to
Yeah.
rail a little bit, but I'm looking on at the mousepad segment, lines 166 through 173.
Mm-hmm.
If I recall, the parameters were 3 trials, choose 5, I believe, or 3 trials with 5 letters of the alphabet.
So with this one, the number of trials is 3. So num trials is 3, and then num choices is 5.
Okay.
Yeah, but this is only a part. This is just a little snapshot of, you know, one particular call from the first invocation to the second to the third. So this is like smack in the middle of something. It's not the beginning.
Right. With the all right. Yeah, of course. So it appears though, we stop invoking function calls. It appears when the number of choices
Number of trials.
trials.
So number of trials and number of choices, or the set of choices, should be parameterized because each invocation has its own number of trials and what choices it has for that trial.
But also, right. That wouldn't work all the time, though, now that I remember, because, of course, we could have a number of trials equal the number of choices. And
Yep, they could
5
equal.
and 5.
Yep, but the number of trials cannot exceed the number of choices. That would not make sense.
Right.
right. Any other questions before we stop today's session?
I'm good.
You're
It's
good?
just that like I did the way I did this is that I actually was able to do it without the trials. Obviously, it was much easier. But when you like have trials,
Mm-hmm.
makes the I don't know why, but I just couldn't wrap my brain around it with having trials, and it was just hard for me. But this makes a lot more sense.
Oh, okay. Yeah, with the trials, that means you can stop the recursion earlier. Except, for that one, you have to run through all the remaining choices that are still available. So for each choice that is still available, you have to print a string corresponding to that last choice from the last trial. Does that make sense?
Yeah, I used a char string for that. So
You
once
can
I
use a
find
char
like the
string.
many,
Yeah.
yeah, and then I redid like the function, the recursion function,
Mm-hmm.
or the permutation function, like I want to say 7 times now. I just went over, and I'm like, oh, this didn't work, this didn't work, and this didn't work, and then I finally like I was like, I'm just gonna redo the whole thing.
Well,
Yeah, I have a lot of time.
that's actually part of the learning process. So that's not
Yeah, I can
necessarily
tell
a
you
bad
what
thing.
doesn't work. That's for sure.
Hey, if we can rule out every single thing that doesn't work, then everything else left would be the ones that work, right?
Yeah, that's a long list though, a really long list.
It's called life experience. When you ask people for pearls of wisdom, that's basically what the answer is. I have tried things that do not work. This is what is left. So I'm changing the due date to next Monday, right? So next Monday is the 27th. There we go.
Thank you again.
Yeah, well, the idea is to give you guys enough time to really do it and understand the concepts involved. Um, I wish I could do the same thing with final exams and all the other exams, but I cannot.
Yeah.
So with exams, I kind of have to strictly say, okay, this is the time frame, and everybody is going to use exactly the time frame, and this is this. But with homework, I can kind of relax it a little bit sometimes, and just so that you guys can have enough time to absorb, what needs to be learned, and then apply it.
Yeah, thank you though.
Yep. All right. So we are almost done with module 0305. Oh, no, not this one, sorry. 0308. So what we'll continue to talk about on Wednesday is really just the binomial theorem, which is yet another proof, like right here. um, it is it's really just algebra, but in this case, it does make certain tricks, in the sigma notation. Um, and also it makes use of Pascal's identity. So Pascal's identity is used as a component in the proof of the binomial theorem. And then we briefly talk about the binomial distribution, which is summarized into this one little single expression. Um, so that concludes discrete probabilities. And then after discrete probabilities, we're going to move on to, we're going to be running out of time, okay, this semester. There's not enough time to cover everything that is on the list. But on the list, okay, the next topic that we need to go over are the time complexity concepts, the big O, big omega, and also the big theta notation. And then we also have graph theory after that, that talks about what is a graph, what it is representing, how do we run certain algorithms in a graph. So those are the two main topics that we have to go over. Um, on the list, we also have predicate calculus. I can kind of compress predicate calculus a little bit, only to the use of Prolog, okay? Because Prolog is the actual programming language that implements predicate calculus. So we can have some fun, just to go through Prolog a little bit, but without a really long and lengthy discussion of what predicate calculus is about. So those are the remaining topics, and I intend to go through those topics in this specific order. If we run out of time, then we might leave predicate calculus out of this semester. So that's kind of the overall plan from here to the end of the semester. So any questions before I stop the live stream? Alright, looks like we are all good. Alright, so I'm going to stop the live stream first, and then the text channel, I will keep an eye out on the text channel for, just on and off in the